Hello everyone, and welcome to Biopedia. We often hear about all creatures great and small, such as in the common hymn, All Things Bright and Beautiful, but the question of how many species there actually are on the Earth has puzzled and exasperated scientists for quite some time. The best we can really do, of course, is estimate, as without systematically eradicating species the moment we find them, it would be impossible to ever be sure that we'd found every species on our planet. As a point of fact, estimates have jumped about all over the place, from values of 5.3 million to about 1 trillion species. As an example, in the 1980s, the entomologist Terry Irwin came up with an estimate of 30 million species, by extrapolating from the number of beetle species he found living on a single kind of tree in the Amazon rainforest. Although I won't go into his full method here, this claim is supposedly controversial, as later figures estimated the number of species as far lower. The estimate I'm going to focus on here is a 2012 estimate by Mora et al., which was published in PLOS Biology. They examined the number of categories present in each of the taxonomic levels down from phylum, apart from species. That is, phylum, class, order, family, and genus from 1758 onwards. This means, for example, that every time a new genus is discovered or noted from 1758 on, the total number of genera goes up, which they represented graphically as number of categories over time. Each of these graphs for each taxonomic rank showed the tendency to level off over time. That is to say, there was an asymptote, where it can be assumed that there are no more categories within that rank left to find. This asymptote approach was used to try and account for any potentially undiscovered categories within each taxonomic rank. The asymptotes for each of these ranks had a value, which at first appears to be wildly different for each level. If these 7 values for the 7 taxonomic groups are plotted using a double logarithm, however, a straight line appears. Now, I'm going to have to explain this briefly, although we're not going to go into a lot of detail. A logarithm simply refers to the power to which something is raised. For example, the log base 10 of 100 would be 2, as 10 to the power of 2 is 100. Similarly, the log base 2 of 16 will be 4, as 2 to the power of 4 is 16. With me so far? Now, the authors used a double logarithm, which means that a logarithm of the logarithm needs to be taken. We don't have to go into all the complex maths of this, so I'm not going to. However, just know that a single logarithm did not produce a straight line for this graph, which a double logarithm did. What this means is, if a straight line can be produced which all 7 of the taxonomic groups apart from species obey, this means that the asymptote value for species can be extrapolated from this. The value that you then get, when you convert back from double logarithms into ordinary numbers, is then the number of species you can predict to be present on the Earth. This is because, as we just said, the asymptote value for species is the point at which you would expect there to be no more species left to discover. So, to summarise, as I know that sounds quite confusing the first time round, if you were to plot the number of categories in each taxonomic group over time, you get an asymptote, at which the graph levels off, and you expect there to be no more of that taxonomic rank left to discover. Do this for all levels, from phylum down to genus, and you can plot these asymptote values. If you use a double logarithm to plot them, you then get a straight line, which you can extrapolate from to get this same value for species levels. This figure can then be approximated, finally, as the total number of species on Earth. The figure that Mora et al. Eventually came up with was 8.74 million eukaryotic species in total. This means that, at the time their study was published, they estimated that 86% of species in total, and 91% of marine life, had not yet been discovered based on this figure. Obviously, there are limitations to this approach, as extrapolation is not a fully accurate approach. Also, this estimate does not deal with the problem of what the ratio of eukaryotes to prokaryotes is, so it cannot be a fully comprehensive estimate of the number of species on Earth just yet. However, it's important to at least have a rough idea. At a time when climate change is wreaking havoc with our ecosystems, it could be important to have at least a rough idea of how much life there really is on our planet. Although we can't be certain, it seems that modern estimates, using our own historical data, might be a step closer. As always, thank you for listening. For any questions, topic suggestions, or general comments, contact us at biopediapodcast@gmail.com. Until next time, have a great week, everyone.